So welcome back. Doing the college algebra thing. We're talking about logarithmic and exponential equations. We're modeling a little bit, and this is a problem that is in our book that I've given multiple times. So this is on August 31st, 1854, an epidemic of cholera was discovered in London, England, resulting from a contaminated community water pump. I don't think they knew that that's how cholera spread at that point in time. I think this is when that happened. Okay, by the end of September, more than 600 citizens who drank water from that pump had died. The cumulative deaths, right? That's the total amount. That's not like a daily count, but that's the whole death count here. At a time t days after August 31st is given by d of t is equal to 91 plus 160 ln t plus 1. Okay, t is in days. Determine the cumulative deaths by September 13th. Okay, so we're going to go here and we're going to, this is a nice, this problem is too kind actually. I don't know if I would give this as a test question. It's too nice. We have 91 plus 160 ln t plus 1. Okay. And then it says, well, how many deaths happened on September 13th? Okay, well, August 31st is really like September 0, okay, because it's the day before September begins. So September 1 is going to be the first day after that. Okay. So September 13th, right, is really when t is equal to 13. Okay, so we're going to go ahead and type that in. So 91 plus 160 ln 13 plus 1, 91 plus 160 ln 14. And are we supposed to round? We're going to have to round because that's not going to be a nice number. Okay, round to the nearest whole unit. Very good. So here we go. We have 91 plus 160 times ln, and then we have 14 here. Okay, this is 513.249, so we're going to call that 513. Okay. Oh, wow, that's really nice of them. They gave us a graph. Okay. What did we say here? That was 513. All right. Oh, please fill in all the empty boxes. They're not going to make us do a little check here. Very good. So the next part is approximately how many days after August 31st did the cumulative deaths reach 550? So what we're going to do, right, is we're going to say this is 550 is equal to 91 plus 160 times the natural log of t plus 1. And now we're going to clean this logarithm up, okay, because again, right, we have this thing going on. We've got to go in that order to start solving. Okay, the logarithm's up here, and then the parentheses at the end, so we got to travel up. So let's subtract 91 from both sides. Okay, so we're going to have 550 minus 91. Okay, we end up with 459 here is equal to 160 ln t plus 1. Okay, let's go ahead and divide out our 160s here. Okay, so we have ln of t plus 1 is equal to, then we have 459 over 160. Okay, we have 2.86875. 2.86875. Okay, well, now we have a variable that's in the logarithm. And how do we get the variable out of the logarithm? Well, we make both sides, right, the base, we make both sides the base to the exponent, okay, and then we'll have t plus 1 is equal to e to this number here, okay. So what we're going to do is we're going to type in inverse natural log, okay, second function, our previous answer, all right, And we're going to end up with 17 points. 17.614. This is going to be in days, so at this point, I don't know what decimal they're going to have, but I doubt we're going to have too many decimal places because I don't think they're going to want this to the microsecond. Okay, this is 16.614 days is equal to t. And what did they want us to round to? Okay, approximately how many days? Nearest, again, nearest whole unit. So 16.6, we're going to call that 17 days. Okay, so that would have been September 17th. Okay, so that was going to be 17, round it up, 17 days. Okay, so that was modeling the cholera in England at this particular time. Okay. All right. All right. So I want to do a couple more word problems before we venture into 3.6, which is also going to have a lot of word problems in it. That's why I have all of these things going on. Here's my PDFs. Okay, or maybe just some random problems. So these are problems I have tormented students before. Okay. And let's see what's going to happen here. Okay. This flavor, number 2, this is one of my most favorite flavors of logarithmic equations because it has all the joy of foiling and raising things to powers and and going back and factoring and then solving. Okay, so it's got all a bunch of moving parts on this problem. This is why this is a good problem. Okay, so what is this? This is the log of x plus 2. Okay, plus the log of x plus 1, and that was equal to, I believe, 1. Okay, so you have to remember, right? What is the base here, right? We know that that's going to be a base of 10. Just noting that because that might come up a little bit later. So you have a rule that says that the log of AB is equal to the log of A plus the log of B, right? Well, that works in this direction too. So what we're going to do here is we're going to make this one logarithm, right? And then we've got x plus, we don't have a fraction. Okay, we're going to have x plus 2, x plus 1 is equal to 1. Okay, now you can go ahead and take the anti-log at this point. It's not going to hurt anything. If you wanted to multiply this out first, that's also not going to hurt anything. So this would be x squared, 2 plus 1 would be 3x plus 2 is equal to 1. Okay. I like to do it this way a little bit more because I think people don't get lost quite as easily if they just have one thing to take the anti-log for. Okay, so that's going to be x squared plus 3x plus 2 is equal to 10. Don't forget the right-hand side. Everybody always forgets this. This is the biggest mistake right here, is not doing 10 to the 1 here. Right? And then we have x squared plus 3x, and then we're going to minus 8, right, is equal to 0. At which point, wow, whoever wrote this problem was a real jerk. Look at this. They can't even factor it. If only there was some kind of a formula we had to like solve quadratics for us. Oh, wait, there is. This one. Okay, 2a really. So we have to go through and do all of that. So actually, I do want to check that first to see if it's greater than 0, equal to 0, or less than 0. Because if it's less than 0, then there's no solution. We don't have to go through all of this. Okay. That's, again, this is called the discriminant. Okay. So b squared is 3 squared minus 4, 1. And this c here, the c carries the negative with it. Okay, so that's going to be a negative 8. So we're going to have 9 minus of minus is plus 32, which is 41. Wow, whoever wrote this really is a jerk. That's terrible. All right. So we have x is equal to negative 3 plus or minus square root. And we've already done this. Okay, we've already done this. We know that this is going to be 41 in here, all divided by 2. Okay, so we have x is equal to negative 3 plus the square root of 41 all over 2. We have x is equal to negative 3 minus the square root of 41 all over 3. Now, negative 3 minus a number, like first let's estimate what's the square root of 41. It's somewhere between 6 and 7, right? 49, we would have a square root of 7. 36, we would have a square root of 6. So this is somewhere between 6 or 7. Let's just call it 6 to be safe. Okay, so we have negative 3 plus 6. Okay, so that's about 3. 3 over 2 is about 1.5-ish. Okay, and on this side, right, we have negative 3 minus 6. So that's negative 9 divided by 3. So that's about negative 3-ish. Okay, so this is why you have to go back and check. So we have about 1.5 or we have negative 3. When I go back to the original equation and put this in, if I put negative 3 into this equation, how am I going to take the logarithm of that, right? Put negative 3 in here, we're going to have like negative 2-ish. But if I try to take the logarithm of a negative number, it ain't going to work. Whereas if I put 1.5 in here, ish, then both of those, we have a positive number plus a positive number. We take the logarithm of that, no problem. Same thing with this. So this one, this is not a solution. Okay, and we come up with the answer of x is equal to negative 3 plus square root of 41 divided by 2. This one works. We checked. Okay. Again, notice I don't want you to have to go through and do this arithmetic and check to make sure it actually numerically works. You don't have to go that far. All you have to do is make sure you're taking the logarithms of positive numbers. Okay, because that also spares, I mean, you can do the whole thing, but it spares you from like not getting quite the right answer and then having to numerically track that thing down. And where that would be good and you get, you know, like actual full credit out of it. But sometimes if you made a mistake in here where you took like say 9 plus 32 and for some reason got 39, like I don't need you to track that down. Right? I'm going to look at that and I say, oh well, that was a bonehead mistake, but I'll just circle it and then I'll just count it right because it's not the kind of mistake I care about. Okay. All right. Nope. Let me go ahead and do that. Okay. Yes, they should. I think that's what we did here. Oh, that should be divided by 2. You're right. You're absolutely right. Divided by 2. This should be negative 4.5-ish. Thank you for that. My handwriting is worse than terrible. Yeah. So yeah, both divided by 2. Thank you for that. Okay. So you bet. Okay. So that kind of is like one of my more favorite flavor. It's kind of a hard one, but that is like the kind. If I can come up with a question that's going to look like this, I really try to make sure that you could factor it, but in this case we couldn't. Okay, so there's other options. This one, okay. Let's see here. We could work this one out for a logarithmic problem. We have log base 2 of x plus log base 2 of the square root of x plus 1 minus 1. Okay, minus 1. Put that in parentheses. And that was equal to 2. Okay. So the first thing we're going to do is, again, we're going to put this stuff together. Okay, we're going to say, well, that's going to, because there's nothing I could do with this, right? It's not the log x, the whole thing minus 1. That would be nice, but we don't have that. So we have log x over x minus 1. Let's make that the minus sign that it's supposed to be. Okay, because that's turning it into a division problem. Right, this is the rule that we're using. But again, that way. And that is equal to 2. Okay. Now what we're going to do is we are going to logify. We're going to make both sides the exponent to the same base. Okay, and why do we pick 2? Because we got log base 2. All right, so here we have x over the square root of x minus 1 is equal to 4. Okay. So here we have x is equal to 4 times square root of x minus 1. Right, and when you have to deal with a rational equation like this, you have a fraction that's in your equation. The first thing you want to do with a rational equation is to make it not a rational equation, which usually means multiplying both sides by a denominator to clear it, because nobody likes to deal with the fraction. So here we have x is equal to 4 square root of x minus 4. And then what we're going to do is we're going to say x minus 4 square root of x plus 4, right, is equal to 0. Okay. Almost in almost all cases, getting the right-hand side equal to 0 before you've done doing anything else to solve it is always a good plan. Well, almost always. Okay, there's certain times where it's a kind of an unnecessary step, but it's never wrong. It's just you might have to go backwards to something else. So getting the right-hand side equal to 0, it's never the wrong step. Okay, here's what we're going to do. We're going to note that the square root of x squared is equal to x. You know, revolutionary. So if I say let u, most books use u. A lot of my students started using u. Okay, you're going to rate u enough in calculus, which is why I usually pick something else. Right? Then u squared would just be x. So here's the problem we have. We have u squared minus 4u plus 4 is equal to 0. I have every confidence that you can solve this problem at this point because this thing factors, right? This is u minus 2 squared equals 0, isn't it? Multiply that out, that's what we're going to get. So now we're going to employ square root principle. So we're going to get u minus 2 is equal to 0, technically plus or minus, but you know, it's 0, so we don't have to worry about it. And then we're going to get u is equal to 2. And then our last step is to note that, oh yeah, u is equal to the square root of x. So square root of x is equal to 2. See, I should have just left it. No, I shouldn't have. And squared is equal to 2 squared. X is equal to, how about 4? So we're good. Okay. Now we're not quite done because we have to put it back into the original thing. So if I plug 4 into my x, do we get a positive number here? Yeah. Square root of 4 is 2. 2 minus 1 is a positive number. Yeah. Okay. So we checked out our terms. 4 works. It is a solution, so we're good. All right, we're good. All right. Let me mix this one off. All right. Let's work on that one. It's an interest rate problem, so it's going to be good. Okay, if you watch Futurama, you will know exactly where I got this problem, because this was actually an episode. So we were talking about compound interest. I said that it's either the interest rate that drives it or the time that drives it. Okay, the compounding doesn't really matter so much, but in this case, a little bit. Okay, so that's actually a really high interest rate, isn't it? Right, these days that's really high. So we start off with a principal of 93 cents, and we're going to let this accrue. Okay, the banks, we're going to assume he didn't bank at Bank of America, so they didn't take a maintenance charge out. He's going to let this interest accrue for 1,000 years, and let's see how much he's worth. Okay, there's a part B that says, what if it compounded continuously, but it's going to be at a little bit less of an interest. So we can compare them. Okay, notice even on this one, I gave, this is a worksheet. They could have looked this up, but I'm going to give you this. This formula is not one you have to memorize. Okay, we might be using it, but you're not memorizing it. All right. So amount is equal to our principal, 1 plus r over n raised to the nt. Okay. So what amount are we going to have? The amount is going to be 0.93, 1 plus. Okay. Here's how you get your calculator blow up. Type in 2.23. Okay. It's not 2.23. It's 0.0223. Okay. Because this is a percent, we have to express it as a decimal. Okay. And then we are compounding it every month, so that's going to be divided by 12. And then up here, we're going to have 12 months a year times 1,000 years. Okay, and let's see what we come up with. So we have 1 plus 0.0223 divided by 12. Okay, then we're going to do caret, and we're going to say 12 times 1,000. Okay, enter, and then times 0.93. Okay, so we ended up with 408,209,896. Okay, we didn't round to the nearest cent because the calculator doesn't do that, but there we go. Okay, so about $4 billion there. 5, 6, 7, 8, 9. Yeah, 4 times 10 to the 9. $4 billion. Sadly, that is the only way I'm going to be able to see $4 billion. But there we are. Okay. What happens if it was compounded continuously, but a slightly lower interest rate? Okay. So we're going to say A is equal to our shampoo. Okay. So what we're going to do, again, we're going to say, well, that was 0.93 here. E. Now this is 0.0222. Okay. And again, times our 1,000 years. And let's see what that comes out to. Okay, so we have 0.93. If I recall, this doesn't really change very much. So E to the 0.0222 times 1,000. Right. In this case, we got 4,028. 332 and 643. So, what's $400 million between friends, right? It's about all we're off. Still $4 billion. So, but yeah, that's what we do. I don't like to give this one as a test question so much because I make a big deal about the fact that you're not supposed to get a big number, and then I immediately lie to you and tell you and give you a big number. But this is also an absurd result with 1,000 years. So it's okay when you get when you type in an absurd number, you should get an absurd result. Okay. So let's see. What is one of the other problems that I gave? This one's sadder. Okay. So I read Radium Girls a couple of years ago. It was fascinating. And if anybody tells you we don't, industries will police themselves. We don't need anything. Read this story. Okay. So, this group of men gathered. I didn't write this. I got this from somebody else, clearly, because this writing is far beyond what I can do. So they gathered on this autumn day, and they were examining her grave because, we'll see in a minute. Okay. So they dug her up, and she was a painter at the radium thing. They would get these really crappy brushes with the radium paint, and the girls were all girls. That's all they hired was girls for this because they were artists. This is the 1920s, but they would dip the brush into their teeth, into their mouth to kind of put a tip on it, right, with their spit, and so they could paint the dials. So they would dip the thing in the paint the dial, put the brush in their mouth, and then dip the thing in the paint again, and on it went. And we now know that radium is not that good for you. Okay, Marie Curie discovered this stuff. They had this pitch, and they took the uranium out of the tar, and then it got more radioactive. Okay, so that was the radium. So not good stuff. But back in the 1920s, we thought it was like a miracle cure. She died at the age of 24, and the USRC said that she's a single girl. She died. It was syphilis. So there you go. Right. Somebody inconvenient dies. They're causing a ruckus. Accused of being a whore, and go about your life. So they opened it up, and the coffin was still glowing because radium lasts for a long time. And then I ask you, how much radium does she still have today? Okay, so she died in 1922, and we're trying to figure out how much radium she has today. So this little bit about 1927 is not, it's flavor. That's not something that's going to matter as far as doing the problem. And I made these numbers up, so I don't know how much radium she had in her. I doubt it was 10 milligrams. Okay, it's probably 10 micrograms. Okay, so we have the half-life is 1,600 years. That being said, Marie Curie's notebooks are still behind a leaded glass wall in the museum. You can't get close to them because they're still very radioactive. And we have a start, right? Our start amount is 10. Okay. So let's see here. We have to. So almost always these problems are like two-part problems. So we have Q is equal to Q sub 0 e to the kt. So the first thing we're going to do is we're going to use the half-life, right, to get K. That's step one. Once we have K, we're going to answer the other question, okay, whatever it's going to be. This one's not quite so bad, but some of them require two kind of hefty calculations. Okay, so let's see here. When I say, see, it was clever. How much will she have today? Meaning this year. You get to use this question every year, and it's always going to be different. So 2021, right? And we have 1922, so that was 99 years ago. Okay. Let's see here. So our time, right? We know that our time that we're going to deal with later is going to be 99 years. All right. if we start with 10 milligrams, okay, e to the k, and we let it run for 1,600 years, how much will be left? And since they were told it's a half-life, your answer is always going to be half, okay? So half of 10 happens to be 5. So let's go ahead and clean this up. So divided by 10, so we end up with 1/2. You should, when you're doing a half-life problem, you're always going to end up with a half over here, by the way. Okay, e to the 1,600 k. Okay, so we've got something that we have to solve for in the exponent position. What should we do about that? Right, we'll take a logarithm. Right, pull this down in front. So we have ln of 1/2 is equal to 1,600 k times the natural log of e, which we know is 1. Okay. Usually what I do here is, right, we solve for k. So I'm going to go ahead and say this is the natural log of 2 to the negative 1, which is negative natural log of 2. Same exponent rule. Is equal to 1,600 k. So usually what I do, because if you try to do decimal places too much, there's big numbers. So I'm just going to call it k for radium and say that's negative natural log 2 over 1,600. And I'm just going to file that away for the next part of the problem. Okay, so when I have to evaluate, I'm just going to type this into the calculator and not worry about what they call intermediate calculations. We're just not going to worry about it. Okay, so how much does she have in her body today? Okay, so same deal. Right. Now we're looking for this number. So we have q sub 0 e to the kt. So we're going to say this is going to be q is equal to 10, because that's what we started with. E to the k sub r, because we're just going to type this thing in when we need it. And I know that we've been going with 99 years. Okay, so calculator-wise, right, we're going to say this is 10 times second function ln. Oops, how about 10? 10 times second function ln k sub r. Now remember, you got to use this formula. You got to use this one, otherwise it's gonna yell at you. So negative natural log 2 divided by 1,600. Okay. Don't close the parentheses yet. Times 99. Okay. You could have said 99 times this thing as well. Okay, that would have been fine. Okay. We should get something that's very close. It's not going to. There's not going to be much decay here. Okay, it doesn't decay very quickly. Okay. Yeah, I really got to fix that. That's like way too much radium. All right, so that's how much we still have. All right, so that's those are the word problems that we're going to be dealing with. Sorry, I'll leave it down there. Those are the word problems that we're going to be dealing with. Get that out of the way for us. All right, but yeah, that's a problem that I wrote. I don't put this on exams anymore because I've noticed students get lost somewhere about here. They're out. I've had several students ask me, like, why did they dig her up? Like, because their family wanted her name cleared. They didn't want to say she died of syphilis. They wanted to, to clear her name. But yeah, that's what's going on there. Okay. Let's see here. We have, I'll let you guys deal with that. Okay. We have, oh, I'm out of time. That's what I'm out. Okay. Window. Let me just take a look at what's coming here. Give us a preview. All right. Last section, 3.6. Oh, we only have 8 questions. That'd be nice. So here we go. This is all the stuff that we just, okay. That's so weird. They put it in a different spot. Oh well. So that's interest rate problem. More interest rate problems. Population. This is a good problem. We'll do that one definitely tomorrow. Carbon dating, radioactive decay, radioactive decay, radioactive decay. I almost always get this problem now. Okay, more radioactive decay. Fantastic. And radioactive decay. I'll have to come up with a, they have a couple of biological growth problems too. Okay. So yeah, that was a prequel to till tomorrow. Okay, that was all the kinds of problems we're going to be solving tomorrow is what we just did. Okay. And my hope is you'll get bored of them by the time tomorrow is over. Okay. So I won't start 3.6 right now. I think we can get through them all tomorrow, but I'll stop there. Okay. So I'm going to go ahead and stop recording.